lecture, you will have let's say we will post a page with all the instruction to download the code. It's already pre-compiled and you can download it with Conda, and you will have a detailed instruction for the exercise. So now you can just sit there and listen to the talk and listen to the exercises and ask questions to the speakers of the day.
Thank you.
Makes sense? Other questions? I just want you to remind you that every lecture is recorded and it will be posted on YouTube. So if you don't want to appear online, just switch off your camera and it's going to be fine. Okay, I think Vittorio can start with his presentation. Thank you very much, Vittorio, for agreeing to do this. It's an honor to have you here.
Thank you, Max. Thank you, Giovanni and Gareth, all the other core developers for this invitation. I'm very glad to be here and contribute for the PLUMED community that I find very interesting and useful to spread knowledge and technical skills to perform many type of standard and advanced simulations. So let me just share my screen and my presentation. As Max already told you, I'm Vittorio Mangeri. I will be assisted by Stefano Ragnolo, who is the project manager in my group. We are going to give you details about technical knowledge about how to perform ligand binding free energy calculation using fundamental dynamics, which is the method that we developed together with Max at the beginning and Professor Parinello at the beginning, and now we continue developing and improving with adding more tools on that. So please interrupt me whenever it's not clear something that I'm going to say to you. Like we have a brief introduction about the methodology, about how relevant is computing ligand binding free energy for many things. Let me first, please, can you please confirm that you can see my slide?
Yes.
Okay, great. And also the animation as well. Can you see also my mouse?
Yes.
Oh, great. Because sometimes it does not work with Zoom. Okay, so why it's important, first of all, if there are many people in the audience that do ligand binding calculations and evaluating of ligand binding modes, the first question is why it's important to take into account the dynamics of a process, because life is dynamics, so running is dynamics, the cell when the device are the dynamics process, and also protein, DNA as well, don't have to be seen as a kind of static molecules like it happens, for instance, the docking calculations. But we have to take into account the possible motion that the residues, the atoms that compose a protein can do, like in DNA or protein as shown in this movie. And in the same time, the interaction between a drug that is shown here as a yellow cartoon on the left corner, well, it's a kind of dynamical interaction. So the first, I would say, concept that should be clear in this talk and this argument is that to have a reliable and accurate description of the ligand-protein binding interaction, we have to take into account the dynamics of the ligand motion, of the protein motion, and also, of course, the solvent effects that play an important role during this type of binding phenomenon. And why this happens? Because so far, still today, many people continue to describe ligand-protein binding interactions as static interactions. People take X-ray or NMR resolved structure of a protein and just do some static calculation like docking calculation, try to predict the binding of a ligand. Well, the result is that if you try to describe a dynamical process, just consider one frame like in these pictures, so the jump of this fish from one bowl to the other, well, you may be afraid that your prediction may be wrong. And finally, the final result is not that is expected by your calculations. And why I'm saying that is that because when you consider the ligand-protein binding interaction, we can think to this process as a chemical reaction in which you have the ligand and protein in the bound state that is in equilibrium with the ligand protein in the complex state. In other words, for those of you that are not familiar with the chemistry, this can be related to the estimation of the binding constant that is given by the ratio between the the concentration of the ligand protein complex and the concentration of the ligand and protein in the bound states. And this is important because the binding constant is a thermodynamic property of the system that is related with the formula that you saw at the bottom of my slides with the binding free energy delta G, which is the, I would say, the goal, the objective of the binding molecular binding simulation that we are going to discuss in this talk. So what this means that if you have experimental values of the binding constant that can come from ISM for your experimental collaborators, it's good to have in mind that in case of competitive inhibitors, this experimental constant can be related using a logarithm conversion into the binding free energy delta G, that is the difference in free energy between the bound and unbound states of your system. In other words, if you have a tool that is able to estimate the free energy of your system in the bound state, where the ligand is in the binding mode in the lowest energy binding conformation, and the unbound state when the ligand and the protein are separated each to the other, if you are able to compute the difference in free energy with that, you have done your work in terms of computing the thermodynamic contribution of the binding process. But there is another important players in the molecular binding interactions, which is the kinetics, because thermodynamic constant Kb and the binding free energy delta G tells you how strong is the binding. In other words, how deep is the basin in which the lowest binding mode occurs. But it's not, this number does not tell you anything about the kinetic. How fast is the binding and how fast is the unbinding of the ligand from the binding pocket. In other words, the estimation of the binding kinetic binding constant K on and kinetic unbinding constant K off is something that is important to keep in mind. It should be taken into account because it tells you how long persists, how long lasts the interaction between a drug and its molecular target. And together, the binding constant Kb and the kinetic constant K off, the unbinding constant is the most important player of the two, are the two most important features and constants that should be computed if you want to perform a third characterization of the molecular binding event between a drug and its molecular target. Of course, you can derive the K on constant from the two constant you have computed, the Kb and K off, using the formula that you can see in the center of my slide. Unfortunately, my mouse is no longer working. I knew that. That's why I prefer to pass to this presentation mode, because now you can see my mouse, right? Okay, yes. So going ahead with the theory, just a few slides of theory. The difference in binding free energy can be computed as the difference in free energy between the system in the bound state and in the unbound state. As we have told you, this is related logarithmically to the binding constants. You can see here, if you describe the free energy as an artistic representation of a reaction coordinate, also known collective variables, that you, for those of you that followed the last year masterclass of PLUMED, you can compute the difference in free energy between the unbound state and the bound state using any algorithm. And I also added the formula here at the bottom. I tell you that you can use whatever methods you want, metadynamics, umbrella sampling, steered, whatever you want. And you can have a look to the review paper that I wrote last year, in which I show you that I just list a number of alternative techniques that allow people to compute ligand binding free energy and kinetics. In other words, it's just important to remind that if you are able to compute the potential and solvation contribution of the binding free energy in the complex state and the bound state through some correction through the rotational and translational degrees of freedom of your system in the bulk, in the solvent, well, you are able to compute finally, use the potential that coming from the simulations, your final binding free energy difference, absolute binding free energy of your drug towards its molecular target. This is exactly the core in which we are going to focus today, which is how we can compute the difference in potential energy or in free energy between the bound and unbound state using metadynamics. Just to place ourselves in a broader scenario of the methodology used, please keep into account that you may use many different techniques. But also keep in mind that the accuracy is always traded for the speed. So if you want to go for a screening of millions of compounds, of course, you are not able to use accurate methodology like those that we're going to see today, but you can go for fast methods, even though those are inaccurate methods like docking calculations that, of course, include some approximation, but at the value of the speed and the reaching of the final results of your project. Now, on the other side, you have accurate methodology that are based on molecular dynamics simulation or Monte Carlo simulations that we can list, we can divide, we can group the different methodology available into the endpoint methods like the line method on PBSA, or the pathway free energy methods like free energy perturbation, thermal integration, double assembly, and also here fundamental dynamics calculation that is the argument and the topic of today's class. So going directly to the outline of the class today, we are going to move the first step into this methodology, advanced methodology, which is called fundamental dynamics. It was originally published on PNS by me, Max, and Michele Parinello. And actually, we are going to see today how we can, I would say in the first 1 hour, the methodology, the theory, and the application of the method. Then we conclude with some exercise that during the week, we hope that we allow you to perform, to run, to prepare first of all, to set up, then run, analyze the fundamental dynamic calculations. And with the help of Stefano, that was the person that developed the protocol that we published on Nature Protocols recently, we are going to see how these different steps that guide you through the use of the techniques are very, very simple and straightforward, and in addition, very rigorous using the methodology that we're going to see together. So in other words, we are going to see the ligand binding free energy calculations, also ligand binding kinetics. You want to compute the K-off starting from fundamental dynamics calculation and using an additional methodology which is called infrequent metadynamics. And also finally, we introduce the fundamental dynamics automated protocol, which is also takes into account a graphical user interface that allows you to set up easily the simulations and also analyze the simulations of the fundamental dynamics that you can run on your workstation on a cluster that is available in your institute. Last, I would say, technical information that I put this red sphere here on the slides when there are some arguments that are important from the theory side or the technical side, and probably most of those have been already covered if you follow the masterclass last year, because you can see here in this slide, I assume all the most important methodology that are going to be treated during this class, which are indeed metadynamics and well-tempered metadynamics, for which I'm not giving to you further details because I presume that you already follow some class, you're already familiar with that. Anyway, you find this red circle here on the slides. So if you are not familiar with the slides, with the methodology that are cited in the red circle slide, please go ahead, go back and follow, repeat the class that you followed last year, or read some papers that I mentioned in my presentation in order to be clear, to be sure that you have enough, I would say, background to follow what's going on with the fundamental dynamic calculations. Just to list, to cite what is important to follow my class today is the metadynamics and well-tempered metadynamics. The concept, the definition of collective variables, you can see we can use in different variants. So what is a collective variable? Which kind of collective variables can be used in this type of simulations? The variational approach to conformational dynamics, also named the VAC metadynamics, which is a variant of the KICA, of time-length independent conformation analysis that we are going to see in the next slides. Fundamental metadynamics, of course. Infrequent metadynamics to compute the kinetics. Path corrective variables that can be used in peculiar case when you have to study peculiar system. We are going to see some examples later on. Multiple worker simulation. You can see more details on that with Stefano during the exercise, and particularly during the correction next week. And reweighting the Boltzmann distribution in unbiased CV space, which is another important theoretical framework in order to perform ligand protein binding simulations with fundamental metadynamics. Just to go directly to the point, what is the problem? The problem you can see, you can already know, is the fact that there is a time scale issue. If you have, for instance, your complex with your drug in your protein in the molecular target, and you run a plain molecular dynamics simulation, you get stuck in one of the minima in which you start your simulation. You are not able, in other words, to cross the energy barrier, to explore the whole free energy surface. In other words, you are not able to identify with accuracy which is the lowest energy binding mode. In other words, which is the binding mode of your drug in the protein binding site. In addition, you are not able to estimate the binding free energy and the kinetic constant that we are interested in order to provide an accurate description of the molecular binding event. How to overcome the time scale issue? Well, something that should be really familiar for you. For those who already follow the metadynamics class, you can pass from a microscopic description of your system based on the atomistic coordinates of the proteins, the ligand, the solvent, of course, to a few collective variables descriptors. So it's a cross-grain description of the free energy, in other words. So still using the Newton dynamics, you are able to reconstruct, using Langevin dynamics, the free energy using a set of collective variables like distance, angles, geometrical descriptors, but even more complex. If you're going to see later on some examples, there are macroscopic descriptors of the phenomenon. And in doing so, we are able to, of course, save time, converge faster, but still we are able to analyze in the microscopic variable ensemble the trajectory by means of modeling dynamics in the space. In other words, we simulate in the cross-grain space of the collective variables, but we can retrieve at any time during our simulation properties related to the atomistic coordinates, in other words, to the microscopic description of our system. This is the trick, the fact to pass from the fine-grained description to the cross-grain description that make this methodology successful in the last 20 years now so far. I want to show you, unfortunately, probably, okay, but you already see many of these of this movie. Well, it's important to remember that in metadynamics, you have to define a number of collective variables, a set of collective variables. Generally, a low number, lower than 3, is advisable to have a convergence in a reasonable time. At the end of your simulation, you have added a bias on the collective variable, so you're able to retrieve the final free energy just computing, just making an integral of the potential of the metadynamics bias that you added to your system. The shape of the bias with the metadynamics is as a Gaussian shape in which the user define the width and the average, the yields that, as you can see in the next slide, but I don't want to go into this detail. In the case of standard metadynamics, the bias rate that can be computed as the Gaussian height divided by the pace, the position stride of your simulations, the Gaussian height never change during standard metadynamics. And in the end, for a very long time, you can have that the free energy is equal to the negative of the positive bias plus a constant. In the latest variant, which is called well-tempered metadynamics, we have a rescaling factor that is represented here of the originally high of the yields. In doing so, we are able to have to average out the error, so to improve the convergence of the metadynamic calculations. And finally, the free energy is computed as a proportional to the bias we had deposited using the formula expressed above, plus product, a constant, which is given by the temperature of the system, plus delta T, which is the bias factor of the simulation that we have set up in the well-tempered metadynamics regime. So these are the two framework which we are going to move. We are going to use well-tempered metadynamics. So you have to care about this way to compute the free energy, to understand how to compute the free energy of each specific states we are going to visit during our finite metadynamic calculations. And now we can move on towards the implementation of finite metadynamics. Why in 2013 we understood together with Max that it was important to develop a fun metadynamics version? Well, because if you perform ligand binding calculation using standard metadynamics, you were able to explore the binding site. But once the ligand reaches the outside, the outer region of the protein, it starts rolling around the proteins and goes in the bulk and never get back. In doing that, you are not able to observe the crossing events between the bound and bound states, with the final results, as you can see here, that if you compute the free energy surface as a function of the distance and the torsion, the distance between the central mass of the ligand, of the drug, and the central mass of a number of residues defined by the user in the protein binding site, and the torsion that CV that describes a relative orientation of the drug with respect to the active site, if you compute this calculation, you will see that the free energy surface in the bulk, in the bound state here, at very large value of the distance, is not flat. It's still rugged, which means that it's not converged to the calculation here. And it's difficult for any user to define which is the reference state for the unbound state, to which you have to compare the bound state to make the difference in free energy, to compute the difference in free energy. So in other words, the lack of recrossing events was the cause of why we did not achieve a convergent free energy surface of the binding event. between a drug and its molecular target. How to overcome this limitation? How to do that? Well, what we thought was that the problems in converging the free energy in the bound region can be solved by applying, and in doing that, probably I can animate my simulation by my presentation by applying a funnel shape potential. A funnel shape potential that, follow me here because it's very important. In the practice, we apply a funnel shape potential in which the center of mass of the ligand is computed relative to the position of this funnel that is placed around the binding site that you want to investigate. But as long as the center of mass of the ligand is inside the funnel, no potential is felt by the system. So the system proceeds as a regular simulations. If you are performing a well-tempered metadynamic simulation, you continue doing well-tempered. If you are doing a standard metadynamics, continue doing a standard metadynamics. If you do unbiased sampling or unbiased MD, it continues doing unbiased simulations. But as long as the central mass of the ligand touch the edge of this funnel, there is a repulsive potential that puts back into the cylinder, in this case, in the funnel shape region. In doing so, the ligand is able to exit and enter several times because we are reducing the region to explore in the bound states. In doing so, we are saving time, we are favoring and get faster the conversion of the calculations. In addition, the fact of using a funnel shape potential allows us to define a number of parameters like the angle alpha, the zeta cc, which is the point in which we convert from the cone section to the cylinder section, and the radius of the cylinder, to be able to customize the shape of the funnel based on the system that is under investigation. Well, during the exercise we are going to do this week, and with our help and advice, you are going to set up the funnel on the system under investigation. Of course, you can set up the funnel on the system of your project, changing and optimizing the values with this graphical user interface that allows to tailor the shape of the funnel on the shape of the cavity that you want to explore during your binding simulations. Well, I already showed you before that absolute binding free energy delta G can be computed with this formula in comparison to the binding constants. Well, if we do all the maths, we can see that the binding constant can be computed with this formula here, in which there are different contributions coming from constrained simulations. And in particular, let's start from the core of this formula. The binding constant is given by the integral in the site, of course, in the binding site of your protein, given by the difference in potential mean force between the bound state and a reference state that can be considered the unbound state of our system. In this case, could be this pose here. In addition, since we are adding an external potential constraint, we have to correct this estimate using two corrections. The first one is equal to 0 if the shape of the cone section is large enough to contain the binding site that is explored by the ligand. In other words, when the ligand explores the binding site, no potential is felt by the system. In other words, the edge of the cone section is pretty far from the region in which the ligand explores all the possible binding modes. If this is the case, this contribution is equal to 0. It does not affect the final estimate of the binding constants. While when the ligand is in a bound state, since the exploration is constrained around this intersection, there is an entropic correction to be taken into account that is equal to the Greek pi product, the square of the radius of the cylinder, because it's the volume, the surface of the cylinder that we are exploring in the bound state. In any case, you can take the numbers coming from the metadynamics calculation, taking this one as the lowest energy binding mode computing your converged metadynamic calculation, minus the value of the free energy in the bound state, and this gives you the difference between bound and bound states, product time the correction, entropic correction coming from this, using this formula, depending on the size of this intersection in the unbound state that you have applied during your metadynamics calculation. In other words, you can rewrite this in a different way, but it's the same. So you can compute the absolute binding free energy with the difference between the bound and bound state, plus a correction that is given as another analytical correction given by the entropic correction due to the constraint of the ligand into the cylinder section in the unbound region. What happens, what you see in your simulations is exactly this. scenario in which the protein shows a cartoon here with the drug and ligand in the red sticks, the ligand leaves the binding site several times, go further back in the solvent, and in the reality, the central mass of the ligands you can see in this movie is constrained within the funnel shape. In doing so, it is able, the drug, to bind and binds several times during your calculation. As a result, all this leads you to have a very convergent free energy surface, and you can appreciate the difference here. If you see the difference, for instance, between this free energy surface, I can do it directly like here. Okay, if you do the difference, you can see the difference here. In the unbound state, look how this is flat with respect to the previous simulation in which the funnel potential was not applied. And this means that your simulation converged. You can take any point in the as a C space as an unbound state, because in the unbound state, all the position of the ligand should be isoenergetic. So it's not dependent by the position of the ligand, the orientation of the ligand that are isoenergetic, which are your reference unbound state. While in the bound state, you take the lowest energy binding mode, which is to which you are going to compute the difference in free energy. In other words, once you have this convergent free energy surface, here is the same, just representing two vertical and interdimensional one, you take the difference in free energy between the bound A and bound C state, and plus the analytical correlation would be to apply a cylinder section of 1 angstrom in the bound region in this case, which is 3.8 kilocalories per mole. If you increase the radius of the cylinder, you explore more. Of course, this correction decreases. That's why it's important. And we demonstrate in our publications that the in silico binding free energy computed with fundamental dynamics fall in the range of previous estimates done by previous calculation experiments. And this was, I would say, the proof of concept that the methodology worked quite well. It was originally published in the original paper. Then it's important to underline that in many cases, in practical cases, it's not possible to just use distance and torsion, but we need to use a more complex description of the corrective variable of the physics of the system. In doing so, you can also use a fundamental dynamic calculation and use a SSCV, not simple geometrical descriptor, but you can use a weighted linear combination of these different descriptors of your system. As you can see here, we apply the so-called VAC meta-D, the variation approach of conformational dynamics to metadynamics, which is, as I told you, is a variant of TICA. So you can perform some correlation metric calculation in order to compute which are the first decaying eigenvectors and associated eigenvalues to the most decaying degrees of freedom. And doing so, you can compute which are the weights to apply to the different descriptors that could be the contact between the ligand and the protein, the solvation of the pocket, the torsion angle of the ligand with respect to the protein, or the solvation of the ligand, and many other, I would say, degrees of freedom, any other descriptor of your system. And so you have in one single CV or two single CV, depending on the decaying time of these descriptors, you can have combined in one single CV many different descriptors that are weighting depending on the analysis of previous or the original or some preliminary calculation that you have performed before running the final production run using the so-called VAC fundamental dynamics calculation. And we have seen here that we're still able to retrieve the binding mode that we found in previous calculation, the benzamide-tripside system, still preserving the right thermodynamics of the system, so identify the lowest energy binding mode, but with a very shorter simulation time that allows us to reach the convergence in the shortest time with respect to the original application of the methodology. And this is a way important when you have, for instance, the problem that your system is so complex that you need to add more and more CV. In many cases, you start with the distance, with a distance torsion, with a contact method, whatever, but finally you see that you need to add solvation and other stuff, and you are not able to keep small the number of corrective variables. So this means that you require a more accurate analysis of your preliminary simulations and to identify which could be the better combination, weighted linear combination of different descriptors of your systems. Well, now passing through from the thermodynamics to kinetics, it's important to underline that in addition to thermodynamics, it's also important to compute the kinetics. We decided with Stefano to define this class mainly concentrating on fundamental dynamics, so on thermodynamics and the, I would say, the procedure to set up a fundamental dynamics production run, how to analyze the binding energy, compute the convergence, analyze the results, extrapolate the binding energy value and the binding modes. But if we have time, in particular, if you are able to pass the first exercise, there will be the opportunity to have an optional exercise that regards how to run, at least, because it requires more computing power, kinetic calculation in order to obtain the unbinding kinetic rate K-off from fundamental calculation. Why it's important to compute the residence time of a drug towards its target? Well, it's important because drug works as long as it is bound. And if you want to perform a lead optimization procedures, which is a practice in medicinal chemistry, which you are going to modify the structure of a drug in order to improve the affinity towards its molecular target, well, it could be that you improve the affinity, the strength, so you can decrease the delta G, but you can also affect badly the transition time. So it's also to keep in mind, it's also important to keep in mind that it's important also to describe which is the rate determining step, which is the slowest determining step, which is the slowest transition that allows you to escape your binding mode and go in the bulk. Because this defines how long the drug stays in your binding site, how long is the resident time, in other words, how long the inhibition, for instance, of that protein occurs in the body due to the action of the drug. In fact, Copeland, in a very interesting review they published some years ago, demonstrate that the in vivo drug the in vivo drug potency of a drug is proportional to the residence time, to the K-off value, more than the KD value. In other words, it's more linear, the correlation between the in vivo efficacy of a drug with the kinetics profile of the binding kinetic rates more than the dissociation constant, which is related to the binding constants. This means that it's good to have description of the strength of the binding, but it's necessary also to have the estimate of the kinetic and binding rates in order to have a reliable prediction of the drug in vivo efficacy, of course, without taking into account the pharmacokinetics and all the stuff that may happen in the body, like metabolism and other stuff that are not taken into account in the case of our simulations. So how this can be done? This can be done using a recent methodology that we developed some years ago. Actually, it was first developed by Tivoli and Parinello, so-called infragram metadynamics, in which if you just deposit the bias of metadynamics with a very low rate, you are able to see the crossing of barrier in a Markovian way. In other words, you perceive the Markovian process of the transition. And if you take into account, if you measure, if you compute, if you compute a running average estimate of the metadynamics bias that you added in the basin before the transition, you can recompute the partition coefficients in the bias ensemble that is related to the partition coefficient in the unbiased ensemble using this formula here that is given by the computation of the acceleration factor alpha given by your metadynamic simulation that is equal to the, as I told you, the running average estimate of the metadynamics bias that you have added to your system before observing the crossing of the transition time. In other words, you collect the time of the transition in the metadynamics regime, you compute the alpha considering the bias that you had added to your system before observing the transition, and you can compute the real time of the transition just using this formula that correlates the acceleration factor given by your metadynamics calculation and the observed transition time that you found, you computed during your metadynamics calculations. To do that, of course, you have to run a number of replicas of the simulation in order to have a statistically meaningful estimation of the transition times. And once you collect all these estimates, you can compute the empirical cumulative distribution function, and you can merge, you can fit this into the theoretical cumulative distribution function, use this formula here, and to compute if the p-value is a p-value which is higher than 0.05, which means that the null hypothesis is confirmed, and this means that you observe a transition which is Markovian. In other words, your transition, your statistics is Poissonian of the statistic of the transition time you collected. In other words, your simulation properly describe the transition over the energy barriers that you are interested in order to compute the escaping time and compute finally the K-off value, which is as a unit per second, because it's of course an estimation of the rate of unbinding of a drug from its binding site. Well, this is what is the theory. And what I can see, what I can show you here, that we apply this theory to many different systems. So you can compute again the acceleration factor from these two formulas I showed you before. You can compute, as you probably will do in our exercise, if you reach the final exercise once you have done all the final dynamics simulations or the final dynamics exercise in this masterclass. You can compute the K-off directly from full unbinding trajectories. As you can see here, this is quite similar to the binding rates that's computed developing a Markov-Stein model in which we can develop a kinetic flux analysis from the different binding modes, different binding minima, free energy minima. You find the fundamental calculation. You can compute the transition between different minima. You identify your original fundamental simulations, and computing this transition between different minima, you can build a kinetic map in which you can compute the flux between the different minima, and using the matrices of these transitions between the different minima, you can compute the negative, the negative largest non-zero eigenvalues of this matrix that give you finally the K-off value of the transition of the binding of your ligands towards this target. As you can see here, if you compute a matrix with different binding states, or you compute the K-off with the one running full unbinding trajectories, the order of magnitude is almost the same. It's important to underline that from this type of simulations, we are also able to identify which are the percentage of the escaping routes followed by the drugs from the binding site. And not only to define the percentage of the escaping routes, but also we are able to identify the saddle points, which is the real transition states between one state, one minimum, and another minimum. In this case, minimum A and minimum P. In doing so, we identify the atomistic structure, we resolve the atomistic structure of the transition state, which is exactly the transition state between A to P or A to B. This is an important information. First of all, this can be validated performing a commuter analysis. So you place exactly to that point, run a number of parallel and batch simulations, and you should find that you have almost half and half probability to fall in the next minimum P or the previous minimum A. And this is a confirmation that support that you really identified the transition states. But it's important to underline that having the atomistic structure of the transition states, like in this case, is a fundamental property of the system because it allows you to plan any modification to your drug that can disfavor or favor the interaction with the transition state in order to decrease or increase the height of the barrier. That is fundamental to have a longer or shorter residence time of the drug in the molecular in the binding site. But these structures, in addition, is elusive to any kind of experimental techniques because these are transient and short-living states that can be identified only through simulations because using crystallography or NMR, these structures are not be detectable. It is extremely important to keep in mind for the future in the next years drug design campaigns because it's something that's very precious and fundamental for a successful drug design. Well, this is another example that I can show you yet also for more complex, larger in size molecules and for another system, in this case was MAP kinases PUR38, we were able to perform the same job to identify different states in the binding site and compute the K-off kinetic value, which falls in the range of the experimental values computed for the same system. Also, in this case, the transition state between the rate determining step, the rate unbinding, no? The determining step, which is TS1 in this case, which is the slowest costing time between the two close minima, was characterized at atomistic level, and this is important, as I told you, for all the suggestions that I give to you for the drug design. Just going very fast to the end of my presentation, just a few examples when finite dynamics can be used. This is an example we published on JAX some years ago that allows to discretize two very small molecules, but with just a difference of a methyl group here. So methyl catechol with respect to catechol, and we are able to discretize difference in free energy, which was very, very small, only 1 kilocal per mole. And this it reflects the same values that was found using NMR experiments. So we were able to validate it, to see and to explain why the methyl catechol was stronger in affinity with respect to the catechol due to the presence of this methyl, because we have a number of hydrophobic interactions here, and this correlation was very impressive. This is important to say that you can use fundamental dynamic calculation to perform SAR studies. SAR study means structure activity relationship studies, in which you have a number of ligands with different substitution and different activities towards the molecular target, in order to suggest to the experimental synthesis to your collaborators which could be the best derivatives to synthesize in order to achieve a more potent drug. Alternatively, like in this case, for the pentameric ligand gate ion channel, you can also use fundamental dynamics in another way. You can use the same drug and you can investigate the affinity of this drug toward different variants of the protein, the wild type, mutant1, mutant2, or deleted form, whatever is important for your study, in order to prove the relevance of that specific mutation, or to explain also some pathological variants of a protein. This is also something that can be done, as you can see this in this study here. But what happens if your protein has a large conformational change? So your protein is so-called induced fit effect due to a drug, or conformational selection as well. Well, this was the case of the adenosine deaminase, in which you can see in this slide that the helices here can belt into an inner position and an outer position. In doing so, the binding site available, the pockets available for the drug binding, pass to be 4 to 2. And in doing so, you have to take into account this motion. And when you have this such a large conformational change of the protein, you can use the so-called path corrective variable. So it's another piece of theory that could be useful for you to get a look. It's not necessary for our exercise this week, but it's good to keep in mind the future, because there are many systems that requires this type of treatment. And without going into the details, you can describe the motion of your protein from a state A to a state B with a number of equally distant steps through a path, and compute this in the shape of a path S and the distance of a path zeta. In doing so, you are able to describe a number of steps that physically brings your protein from state A, like the closed state that I showed before, to the open state, with something that could be also a kind of geometrical interpolation. So it could be a fake initial gas path, because since you're also sampling the zeta space, which means the distance from your reference path, you can, starting from a very badly built gas path, and find the lowest energy path from state A to state B that allows you to see what happens when the ligand, the drug, enters into your protein, and the protein accommodates the ligands, assuming different alternative orientation, positioning of the backbone atoms, for instance, in the case of a helix that is moving, I can show you in a while. In other words, you want a system that passes from base A, from state A to state B, and can follow different pathways in the free energy landscapes you can show here. And you just give a reference path with equally distant points that separates intermediate frames between state A and state B, and you then run your simulation and find, and you can see in this movie, you can see that the yellow helices can open and close several times using the path corrective variables, and in doing so, the ligand is able to enter and exit and binds the binding site and identify the right positioning in the binding site. In doing so, we are taking into account the configurational entropy or conformational entropy, how you prefer to call it, of the protein during the ligand binding mode, which is an important issue in binding free energy calculations. As you can see here in this slide, the X-ray structure that was resolved before was the orange and the green one. With the meta-dynamics, we found a yellow one, which is a slightly open, because this slightly opening was due to the presence of these specific ligands that enter here and induce this conformation rearrangement of the protein. It was taken into account and was described correctly by the path corrective variables. In addition, the ligand is able to perform this water bridge interaction, as you can see here, between the drug and the protein. Is another important concept in this type of simulation, because in many cases, water molecules play an interplaying role between the drug and the proteins. And being able to assess this interaction is fundamental also in terms of contribution of energy. And this is possible, for instance, using any reweighting algorithm that you prefer. In this case, I report that one that Max developed some years ago, in which you can compute the Boltzmann probability distribution for CVs, that corrective variables that were not biased during your original metadynamics calculation, and you can recompute the probability distribution in this case. And as you can see here, using, for instance, corrective variables called interficial water, which is just a combination of coordinating waters around the drug and the protein, you can estimate the contribution in free energy when the ligand is bound, so with a low distance value, and the interficial water is higher number. This means that you have at least one water molecule that makes a bridge between protein and the drug, and is given this contribution here. And this is important because in this case, you are going to characterize, to estimate how strong, how important is the presence of the water in your ligand binding mode. And this is important, of course, for drug design, any kind of derivation you can have from these studies. Well, this is another example that fundamental dynamics can be used also to study ligand DNA interactions. Also, in this case, the important contribution of waters, even though you have both a water presence, but also water absence in this case, once you reweight along the distance or the torsion in this case, and the water interficial collective variables. Finally, and going finally to introduce you the protocol, you can also study the interaction between a drug and the diffusion into membrane bilayer, how this drug works as, for instance, an allosteric binder here in the extravestibular binding site of this GPCR in the membrane plane. And you can study not only the diffusive motion of the drug from the bulk to the membrane, and then finally how it reached the final binding site through a three-step mechanism in the binding site with a good, I would say, very good superimposition with respect to the X-ray pose. As we can show, as we can demonstrate in the last example, for a drug sites ligand, we can also see how the binding of allosteric site can induce a different shape of an angstrom long distance at ATP binding site in the case of its short protein 19, in which a convergent binding simulations allows you to perform a dynamic cross-correlation analysis, in which you can observe that the binding in the allosteric site here, probably there's a movie that shows better than words, the binding in the allosteric binding site here induce a shape change in the protein at a region of very distance from the ligand binding site. This is also an important aspect that you can take into account. In other words, you apply your funnel here, you study your interaction here, and then you can study performing time series analysis to investigate, to characterize long cascade motion of the binding site of the ATP in this case, which are different angstrom far from the binding of the ligand that occurs during your simulations. Okay, I think that this is a quite nice and exhaustive overview of what is possible, what is the power of the methodology. Briefly, before leaving the lead of the discussion, the word to Stefan that is going to introduce you the exercise. Of course, the question that you may have before moving to the presentation of the exercise, let me just show you the protocols that we published last year on the issue protocols of the Fundamental Dynamics Advanced Protocol FMAP, in which you are going exactly to reproduce the same 3 steps during this week. So please read carefully this protocol paper, because in this paper is basically is reported exactly the exercise you are going to do during this week and all the things they are going to show you. So fundamental dynamics set up as a pre-processing, of course, phase, the simulation that you can run kindly using the code that Max and Giovanni make available for you, and post-processing that allows you to again to our the graphical user interface that we develop using VMD, you can analyze your results. In other words, very briefly, you can see that you will have this graphical user interface in which you can just change. You are going to do this exercise, so just for you, just to anticipate and to show you today what you're going to do during the week. You have your protein showing as a cartoon. You are going to use this graphical user interface in which you pick the atoms and define the right shape of the funnel towards this protein. And you can define, as I told you, the position of point A, point B, that define the axis of the funnel, the alpha, which is the amplitude of the consection, the CC, which is the switching point between the consection and the cylinder region, and all this stuff. As you can see, the change in this point may change also of course, the occupancy of the funnel into the space, the three-dimensional space. And the nice thing of this GUI is that once you have set up all these parameters, with just one button in the, as is reported here, export, you can download already the file prepared to run the simulation with PLUMED. So you already have the input file prepared to run your funnel dynamic calculation on the system. This is the supercomputing center in Lugano, but you can run the simulation in the workstation that is available for you. And finally, you are going to analyze your results using VMD, in which you have this a second graphical user interface, in which you can see your free energy surface. You can extrapolate and save the PDB structures from your trajectory that represent the lowest energy binding minimum. You can compute also the reference value for the unbound state and the bound state, and finally get a calculation of the binding free energy value of your systems. And you can do many additional, you can see here, this is an example in kilojoule per mole. You can have many other possibility to analyze your simulation, computing the error using block average analysis, all the things that Stefano is going to present you that are not reported, of course, in this movie. And finally, the final goal, as you can imagine, is to have a very detailed description of the drug binding towards its molecular target, with the description of the direct interaction, the water-mediated interaction, and also the transition states I told you, if you also are able to perform kinetic calculation with infrared metadynamics. Okay, I think that it's enough, and we are on time. Okay, you can find, again, the literature, so please read the original paper on PNS and the Nature Protocol paper to get the information required to do the exercise this week. And of course, PLUMED Nest, in which you find the code and the sample inputs for this type of simulation. But of course, you will have our guide during this masterclass today. Well, I'm just reading the chat. So first of all, I would like to ask if there's a question from the audience.
Vittorio, to interrupt you.
Yes.
Sorry, it's Giovanni here. Can you hear me?
Perfect.
Hi, how are you?
Fine, thank you. Everything is okay?
Yeah, so sorry for the delay. So since I was not here at the introduction, I wanted to just welcome everyone, and I will not waste your time because I'm sure that Max already explained everything. Let me just add that I sent to the chat a link where you should register if you want to have access to the Slack channel to interact with Vittorio and with Stefano during the week. And that's it. Then I guess you can have a discussion time with Vittorio if Vittorio is available. And
absolutely. That's why we start 10 minutes later. So I think we have 5-10 minutes for discussion, of course. And also I would like to leave the word to Stefano that's going to introduce the exercise a little bit. And of course, we are available all the week, no problem. But okay, first, let's see if there is question.
Yeah, the full presentation is recorded on YouTube. So just so in case I have to leave and Stefano needs a lot of time for explanations, just end the meeting and the recording will stop. So thanks a lot.
Okay. Is there any question, guys, from the audience?
I have one question.
Please. Who is Ramin?
Yes.
Nice to meet you.
Nice to meet you. Thank you for the great presentation. Just one question in the practical part that we wanted to, for example, define the funnel shape and the location of the ligand and the software that you introduced us. Is it a free software that we later can use or it's just, okay. So
everything is free. Okay. Everything is free.
Okay, thank you.
Now and forever.
Thanks.
hope. Any other question?
Hello, am I audible?
Yes, I can hear. Shaunak.
Yes, that's correct.
Nice to meet you.
Thank you for the presentation. My question was that in the equations you had mentioned that there is a WZ PMF which you calculate to in order to calculate the binding constant Kb, right? So in order to do the funnel metadynamics calculations, do you have to do a metadynamics calculation before in order to proceed with the FM calculations?
You refer to the equation that I showed you for the calculation of the binding free energy, right?
Yeah, so the equation I'm referring to is Kb is equal to E raised to
yes,
beta.
no, you don't need to do anything. You can do this post-processing using our GUI. You just run your metadynamics calculation, well tempered, and finally you get the free energy value between bound and bound state, and then you can correct this analytically in the post-processing phase.
Okay.
So it's straightforward. You are going to see this is part of the exercise. It's something you do post-processing in the post-processing phase, and it's very straightforward. It's just an analytical correction. In addition, the entropic correction is a fixed amount because it's defined by the radius of the cylinder that is not a variable. It's defined at the beginning and is fixed during your simulations.
Right.
Okay.
Thank you.
Hi, I have a following up question. Sorry.
Please. Palomino.
Sí. Hola. Yeah.
Hola. ¿Qué tal?
Todo bien, gracias. No. So in the analytical correction that you have over there, I see that you put like the volume of the cylinder, right? I see that, but I don't see that you are putting the conical section of the.
Yes, you are right, because the conical section should be purposely chosen by the user in order to include the binding side. In doing so, the exploration of the binding side is free. It's not affected by the consection.
Okay.
It's large enough to include the binding side. And please remember that when the ligand is inside the funnel, no external potential is felt.
Okay.
You're just performing a regular simulation, metadynamics, molecular dynamics, umbrella, whatever you want. You just apply correction as soon as the system feels the external potential. This happens only if in the bound states, if you purposely choose the amplitude of the consection. Of course, if the consection is too narrow, and yes, the sampling of the binding site is affected by the presence of external bias, you have to also take into account this correction. But it's smart to avoid this.
Okay, so then I should set this angle alpha or something wide off, so the ligand can actually get straightforward, something like that, right?
Right.
Great.
Right.
Thank you.
That's why we allow with the graphical interface to customize all these parameters in order to, to put the funnel in the best positioning with respect to the system under investigation.
Okay, great. Thank you.
My pleasure. Other questions?
Hi, this is Sumit. Can you
Sumit.
hear me?
Yes. Sumit.
Thanks for the great talk. Thanks for all the explanation. So I was wondering, like, if suppose you have a system of protein and ligand in which you have multiple pathways through which a ligand can approach a binding site, then you will probably have to define multiple funnels to get free energy along those pathways. So, but before that, we'll have to figure out what are all the pathways. So do we have to do some simulations before we actually do the funnel simulation to identify all the pathways? Do you have any suggestions for that?
It's a very, very interesting question because they may occur, of course. There are cases like that. In particular, kinase, based on my experience, we have two channels. So you can perform two independent funnel simulation in which you just compare the lowest energy pathway. It's one possibility, one answer. With Stefano, we were working on a kind of double funnel at the same time. It's one single simulation, but at the moment it's not available yet, the code. So you can run independently two funnel dynamic simulations. And if you want to have a faster and not, I would say, quantitative results, you can perform some molecular dynamic simulations, which is faster and allows you to have some hints about the possible exit pathways And then you can place the funnel in independent simulation in order to have the productive simulations on the most frequent exit pathways or entry pathways.
Thank you.
My pleasure. I see other hands raised. I don't know. Ron C. Ramin, probably you forgot to lower your hand, or you have another question, or no?
I have another question, but Ron, I think is
Ron is first. Yeah. Please, Ron.
Okay, yeah. So one thing I found really interesting is obviously it's quite a visual inspection you can get of the transition states. Do you see any potential, or has there any situations where people have analyzed some of the transition states, especially some of them preceding exiting the active site, to maybe optimize the ligand using SAR to kind of hold it in there, or to kind of maximize some of the interactions there, or kind of put a hold on it?
Can you please repeat your question? Because I think I understood, but I want to be sure.
Yeah, so basically, is there any potential SAR to be done using some of those transition states, not just the most commonly occupied?
I understand your question. So your question, if there exists any example literature, people that exploit this, right?
Yeah.
No, not yet. Suppose that the Rio Copeland, just think of 5 years ago, this simulation was quite expensive, time demanding. Me as developer of the infrared applied to ligand bind simulation, we just have 3-4 papers out. There are other techniques, of course, that also can be used to compute kinetics, Markov state model with ensemble. So there are many, but still are very time demanding. And people that used to do this simulation are physical chemists, not medicinal chemistry. Medicinal chemists continue using docking, this kind of stuff. But of course, it's good, as I told you, for a specific aim, but they are not accurate, rigorous. So to answer your question, this is the future, Ron. This is the future for people. Of course, also the I would say the demand, the computing demand of this calculation will be improved with the supercomputer center, a supercalculator. Now we are able to do so, but still, to be honest, the competition with docking is very hard.
Yeah, thank you. That's a great answer.
Thank you. Rami, second question.
Yes. As a follow-up question about different pathways, so is there any, how flexible is this method to define imagine we have a 2 binding site in the protein location, and we define one unbounded state, something like this, to have 2 funnel, one to the other binding site, the other one to the other binding site, and having one bounded. It's like a dilemma that can goes to that direction or goes to this direction, to find the free energy difference between those 2 binding sites.
Well, this method, are you finished?
Yes.
This methodology allows to compute the absolute binding range. So once you define the absolute binding range of one binding site, and you compute the absolute binding range for the other binding site, you already know which is the lowest energy binding mode, and then it's a matter to also identify which is the lowest funnel. Yeah. Because it's faster. Yes. You can also connect, but it's faster, and then you have reference value is the same. The unbound state for funnel simulation 1 and simulation 2 is the same. Both are the same reference bound state, unbound state.
Yes.
And since you are computing the unbound, the absolute binding free energy, you can easily to compute also relatively the binding 1 and binding 2, binding mode 1, binding mode 2. Okay. Cool. Additional question, guys? It seems not. So, Stefano, are you there?
Yes, I'm here.
So let me introduce Stefano Ragnolo, who is responsible for the development maintenance of the fundamental mechanics of the advanced protocol, and is the project manager in my group, and is the person that will give you all the technical links, skills. He knows better than me all the I would say lines of the code and this kind of stuff. So Stefano, please take the lead and introduce the exercise and tell the people what's going, what they will, what are the things they are expected to happen in the next week.
Okay, so can you see the my desktop? I shared the screen. Can anyone confirm?
Yes.
You can see it.
Yeah.
Okay, so when it will be completely ready, because we are still changing some stuff, you will have a page in the tutorials of PLUMED, which will be called the Masterclass 22.1, introducing funnel metadynamics. As well, you already heard by Professor Limongelli all the things that you will do. I will just go a little bit deeper in the requirements for the softwares that you will need. So Professor Bussi and Professor Bonomi prepared already a Conda environment, as they said. Inside, you will find all the GROMACS and PLUMED that you will use for part of the exercises. The other thing that I would require for you to do is to download, which is, I'm sorry, it's written here, okay? I don't know if you are familiar with VMD, but we used for the graphical user interface VMD, so that is compulsory. It is free software. You will have just, if you never downloaded it, you are just to create a user in their website. But if you specify that is for Academy, you will not pay anything. So I need for you to download VMD, and then the interfaces are given in a GitHub that you will find on this website here. And here are all the information to load the interface. As you already understood, we will analyze this system here, which is the benzamidine trypsin system. And this is the example. I will have to change the dimension of this image. However, this, for example, is one of the interfaces. This is on the right, the visualization window of VMD. So everything that you will do on the interface will change automatically and interactively to the visualization window of VMD. And the first exercise will be exactly that. So using VMD to create a canvas, which is what you find here, which, if you recognize it, is a PLUMED input file. So with this interface, we will create a personalized and customized PLUMED input file that you will use in exercise 2 to run funnel metadynamic simulation. So you will have to have a basic grasp of what all of these parameters are. There is some explanation in the documentation for the tutorial. More data will be present in the protocol that Professor Limongelli told you to read. If you have problems to acquire the document, please contact us, and we will provide more information. Then with the input done, this can be exported on a TXT file. With the input done, we will provide a TPR because we are going to use GROMACS. So we are expecting for you to have a basic understanding of the files that are necessary to run a simulation in GROMACS. We will provide you with a TPR, and the input file you have to generate from exercise 1. You will launch the funnel metadynamic simulation. I would suggest you to, as soon as the tutorial page is online, I would suggest for you to start as soon as possible, because as Professor Limongelli said, this is a simulation that requires some statistical data, let's say, to be sound and to provide accurate estimate. So if you do the simulation only on the last 2 days, the quantity of steps that you can run will be too low for an analysis. But here you will have all the commands that you have to launch, and some controls that you can do to check convergence of the simulation. The exercise 3 will be a post-processing one, where we will see how to obtain from a funnel metadynamic simulation an estimate of the binding free energy. Like in this case, you have the value here, but we will also see that this is just part of the calculation. There are some checks that you can do to better see if your simulation is convergent or not. And in the end, also, we will do a basic analysis of the states that we obtain with some commands to align your simulation and so on and so forth. So here you will need GROMACS and TrashConv, more specifically, and VMD to do that. And then we will finish with the exercise 4, if we have time, where we will see a basic how to proceed if we want to pass from funnel metadynamics to infrequent metadynamics. So extracting the transition state or calculating the K-off and so on and so forth. I would like for you to have a look when it will be ready at the tutorial. So if there are any question about the hands-on practice, so for example, the softwares, what you need to have and so on and so forth, this is the time. Do we have any question?
So I have one question.
Yes.
So these files are for the GROMACS, as you said, but if you wanted to use different packages, Amber, so we can skip a couple of those lines, but files are ready to run simulation on Amber or everything.
Well, if you want, if you want to launch a simulation with Amber, the main difficulty that I can see would be that you do not have the topology file and the coordinate files, because I will give directly a TPR. So you would have to extract the information from the TPR. Otherwise, we can transform, if you want to use Amber, we can transform in PalmTop and input CRD.
It would be great if you can have a, if you have a ligand PDB file and the protein PDB file putting in that location, and then I can generate the topology file and the coordinate file to run the Amber. But I was wondering, if we don't want to switch the GROMACS, since we have only 1 week to run this simulation.
Well, in theory, GROMACS would be the most performing choice that you have. With Amber, you will be slower, just for the effect that PLUMED uses, or at least I'm not sure if it changed. From what I know, it uses only 1 core, with especially if you call PLUMED CUDA, which just use 1 core, and there's no GPU in part in PLUMED, so you will be slower in all the calculation of PLUMED.
So for the PLUMED in funnel, there is no GPU, because I'm running with the GPU on Amber using PLUMED metadynamics and well tempered metadynamics.
You will still be using GPU for the part in Amber, so PME and everything else will be offloaded to the GPU. But as for all the calculation of PLUMED, I think that everything will go to the only CPU that you provide to PLUMED CUDA. Which I guess will become the bottleneck of your simulation. And one other thing you cannot use, because in here in exercise 2, you also have the information if you want to use. This should be somewhere. Well, it is somewhere here. The information to use the multiple worker with GROMACS. Thing that is cannot be done in Amber, or at least not in the same way as GROMACS does. So we can still use Amber. Just be prepared that I think that you will have bad performances.
Okay, thanks.
You're welcome. Another thing, the Conda environment will only have GROMACS, so you need to have a working version of Amber with the version of PLUMED patched to Amber, which is superior than 2.7.
Yeah, I do have that.
Okay.
Yeah, I am working with that.
Ramin, what I would say is that, of course, you can run Amber in the future with some checking of the technical things that Stefano mentioned. I think for the sake of this exercise, even though you're not familiar with GROMACS, but you're familiar with Amber, with an MD code, just a matter to run the calculation and follow the instruction of the document. I don't see difficulties in doing that, because the files are already prepared for you. In addition, you can ask for some help to Stefano that provides you some hints for the GROMACS calculation.
Okay, thank you. That would be, I will try. Thanks.
We can also, in case, we can also try to optimize with Amber afterwards in Slack.
Okay, it would be great. Thanks.
I think there is Anya. There's a
Yes.
raising hand.
Yeah. Hi. I
Hi.
have a question, and I'm running on Gromax, and well, I'm quite new, but I have different versions of Gromax and patched with PLUMED on the cluster and on my computer because I compiled it myself. So on the cluster, it depends on where I'm running it. I do not control the version, so this will run. It's compatible among versions.
Generally, you would find that Gromax complains quite a bit if you try to provide a TPR generated with one version and then you try to launch with another version. The one that is prepared by me, the TPR should be 2020.6 of Gromax. PLUMED has always to be 2.7 point something, because from that version onwards, the module of the funnel has been added. So we cannot use any version of PLUMED that is prior to 2.7. So from 2.7.0 onwards. If you have 2020 with PLUMED patched 2.7.1, it's fine. If you have another version of Gromax, we can try to launch the same TPR. If it complains or it crashes, might be for that reason. But in the case, we can just provide the grow and the top that we used to generate the TPR, and with your MDP, one MDP created on the spot, we can solve the problem.
Okay, because I have on my computer the latest version, because I just started with Gromax and PLUMED. The problem is the cluster, possibly. I don't think I can run a simulation that long on my computer. So I have to check, and if I have problem, we probably need help.
Yes, it's also written in the tutorial. Please don't try to run these on like laptops or something like that, because you will reduce very much the life of your PC.
Yeah.
So if you have
I
like
know the problem, I do not control the version on the cluster because I don't manage it.
Well, if you have like because going too much on previous versions might be more of a problem than going to more recent versions. So let's say if I create a TPR with the 2020, might not be a problem to run with 2021, but might be a problem to run with the 2019.
Okay.
So we have to see. It is always better if you have a conflict with the different version of Gromax. It is always better to create the TPR, so launch again the gromp, but with the gromp of that version.
I have to check if it is 2020 or later, and 2.7 the PLUMED.
Yes.
On the cluster, of course,
yes.
Because the other, I have it. Okay, thank you.
Any other version, we will solve in Slack, I guess.
Okay, thank you.
You're welcome. Any other question? I guess there are none.
Okay, fair enough. So I hope that you enjoy doing funnel metadynamics. Okay, anyway, we are in contact on the Slack channel, and in any case, see you next week, next Monday, right, Stefano?
Yes, I guess so. And if you have any question, I think that the channel in Slack has already been created. You will find the tutorial as soon as possible. We are still working, tweaking the last bits of the tutorial, but by tomorrow you should see the tutorial on the official PLUMED website.
Well done. So have a nice evening to everybody. See you next week.
Bye all.
Bye.